So here's part 2 of the grade 12 advanced functions exam review. So in this section it's going to be all about trigonometry. And in the trigonometry unit you would have done everything not in degrees, but you would have done it in radians in this course. So what is a radian? One radian is a way of measuring an angle where the arc length, so this length here, is equal to the length of the radius. That is 1 radian, when the arc length equals the radius. So how many times does this radius, this length is equal to the radius, fit around a circle? Well, hopefully you remember the circumference of a circle is equal to 2 pi times the radius. So that means the radius goes around a circle 2 pi times, which means in a circle in 360 degrees there are 2 pi radians. And we can use this property to switch between degrees and radians, and or from radians to degrees. So if we want to go from degrees to radians, so if we want to convert from degrees to radians, we must multiply by pi over 180. If we want to go from radians to degrees, we have to multiply by 180 over pi. So let's practice those two things really quickly. So if we have 3.62 radians, well, how many degrees is that? Well, I'll just multiply by 180 over pi, and that will tell us that we have 207.4 degrees, approximately. Let's go the other way. What if we have 45 degrees and we want to go to radians? Well, you multiply by pi over 180. And the nice thing about radians is we can leave our answer in exact form, which is why it's beneficial to use radians, right? We don't have to give this approximate rounded decimal like we did with degrees. What we can do is we can actually give an exact answer here. So what we do is we just reduce 45 pi over 180. And 45 goes into both 45 and 180. It goes into 45 once, so leave 1 pi. And it goes into 180 4 times. So what we have is pi over 4 radians, an exact answer. So in this course, you would have worked exclusively with radians. So it's good to know how to convert from degrees to radians by multiplying by pi over 180. And you would have used your same two special triangles as you would have used in the functions course in grade 11, but this time we would draw them using degrees. So you would have your isosceles special triangle where these two sides are the same, which meaning these two angles are going to be equal to each other, and they're both pi over 4. They're both 45 degrees, so pi over 4 radians. And these sides, 1, 1, root 2. And then we have our half equilateral triangle. So our half equilateral would have had a 60-degree side, which is an angle of pi over 3 if we're in radians. And this would have been half of pi over 3 since it was an equilateral cut in half. So half of pi over 3 is pi over 6, or 30 degrees. And our equilateral was a 2 by 2 by 2, so it was cut in half. So that's still 2, but this one's half of that 1. And the Pythagorean theorem would be able to get us this, root 3. So these are our special triangles using radians. You'll need to know these for a good portion of the rest of this unit. So what if we want to figure out an exact value for a trig ratio? So sine of 5 pi over 3. So we have our grid here. Note this is the initial arm along the positive x-axis, so this is 0 radians. And then this would be, if we're going to rotate, so a positive rotation is counterclockwise. This is 90 degrees, or in this course, pi over 2 radians. Then 180 degrees, which is pi radians, then 270, which is 3 pi over 2 radians, and then right back to the beginning, we'd have gone a full 2 pi radians around the circle. So 5 pi over 3 is really close to 6 pi over 3, which is 2 pi. So what we did is we went around the circle and fell just pi over 3 short of going a full 2 pi. So 5 pi over 3 is in quadrant 4. So this is 5 pi over 3. And if we're going to find the exact value for sine 5 pi over 3, we're going to need to know the reference angle of 5 pi over 3. So the reference angle is the angle between the terminal arm and the x-axis. And I typically call that reference angle beta. And if we want to calculate beta, I'll just do it off on the side here. Beta equals, I need to find the difference between 2 pi and 5 pi over 3. So 2 pi minus 5 pi over 3. Now 2 pi, written with a common denominator of 3, would be 6 pi over 3 minus 5 pi over 3. So beta, my reference angle, is pi over 3. So the reference angle, pi over 3. So if I want sine of 5 pi over 3, I can use the reference angle, but make sure you remember cast rule. See, A-S-T. I'm in the cosine quadrant, which means only cosine is positive here, so sine has to be negative. So if I want to find the exact value of sine of 5 pi over 3, I can use the reference angle, sine of pi over 3, but I have to remember I'm in the cosine quadrant, which means sine is going to be negative. So I'm going to have negative sine pi over 3. So pi over 3 is a special angle. Look back to your triangle. Sine is opposite over hypotenuse. So here's pi over 3, opposite root 3, hypotenuse 2. So I can use that special triangle, and I get negative root 3 over 2. And you could check on your calculator. Your calculator will give you an approximate answer. Type sine 5 pi over 3, type negative root 3 over 2. They should be the exact same approximate answer. What if we want to graph a transformed trig function? So I've got this transformed cosine function. If I want to graph that function, I'm first going to state some properties of this function. The amplitude is equal to the absolute value of A. Oh, and remember the parameters for transformations. A would be in front, K and D are in brackets here, and here's C. Those are the 4 parameters for transformations. So the amplitude of a trig function is equal to the absolute value of A. So A is negative 1. The absolute value of negative 1, in this case, is 1. Period is always 2 pi divided by K, right? The period of cosine is 2 pi, but K value is going to do a horizontal stretch of compression. So 2 pi over K, or over the absolute value of K, I should say. So 2 pi over 2. In this case, this function just has a period of pi, right? It's been horizontally compressed by a half. So instead of a period of 2 pi, it now just has a period of pi. It'll do 1 full cycle in pi radians. Phase shift means left and right. So our d value is pi over 6. So we go pi over 6 radians to the right. Vertical shift, that's based on our c value. The vertical shift shows us where the middle of our function has moved to. It's up at 3 now. So we have to move 3 up. To get the max value, you do your c value, which is the middle of the function, plus your amplitude. So plus the absolute value of A, right? Amplitude is the distance from the middle to the top or bottom, right? It's half the vertical distance between max and min. So to find the max, you go to the middle of your function c and just add the absolute value of A. So in this case, c is 3, and our absolute value of A is 1. So the highest the function will go is 4. The lowest, you go to c and then subtract the absolute value of A. So 3 minus 1 is 2. The lowest the function will go is 2. Now let's actually graph this function. So usually how we do the graph of this function is we transform the points of the parent function cos x. So remember cos x, just some key points for cos x, just go at pi over 2 intervals, so 0, pi over 2, pi, 3 pi over 2, 2 pi. And for cosine, it starts at 1, down to 0, down to negative 1, 0, 1. If you forget these values, you can use your unit circle, or you can ask your calculator, cos pi over 2, your calculator knows it's 0. If we want to graph the transformed function, we'll do the proper transformations to these points. So what's happening to x? It's being horizontally compressed by a half and right pi over 6. We have to do x over 2 plus pi over 6. So x over 2 plus pi over 6. So I'm going to do these transformations to these points. And what did I call this function? G at x. So this is the table for g at x. What's happening to y? So what vertical transformations? Vertical reflection, up 3. So I need to do negative 1y plus 3. So I'm going to do the transformations to y first. So plug in these y values into this little equation we made. So we'll get 2, 3, 4, 3, 2. So those are the y values for our transform function. If we want the x values, we'll plug these x values into this little equation we made. So the first one will give us pi over 6. And then the next one, if we plug it in, pi over 2 is pi over 4. So I'm going to have to do pi over 4 plus pi over 6. That would give us 5 pi over 12 if we get a common denominator. So 5 pi over 12. So this is a 2 pi over 12, then 5 pi over 12. So it's going up by 3 pi over 12 each time. So next is going to be 8 pi over 12, and so on. But if we do the actual calculation, so plug in pi over 2 plus pi over 6, that's 3 pi over 6 plus pi over 6, that's 4 pi over 6. which is 8 pi over 12. And then if we keep going, we would get 11 pi over 12, and then 7 pi over 6. What we're going to want to do to be able to graph this accurately is we're going to want to convert each of these to have the same denominator. So let's figure out whether we want it to be a denominator of 6 or 12. So if we want it to be 12, well, this is a 14 pi over 12. So do I have 14 tick marks available here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I don't. I only have 12. So I'm not going to be able to go up by pi over 12. I'm going to go up by pi over 6 because I would only need 7 tick marks. 1, 2, 3, 4, 5, 6, 7. Good. So I'm going to go up by pi over 6. So 1, 2, 3, 4, 5, 6. That would be 6 pi over 6. So this is pi. 1, 2, 3, 4, 5, 6. That would bring us to 12 pi over 6, which is 2 pi. Same thing the other direction. 1, 2, 3, 4, 5, 6. There's negative 6 pi over 6, which is negative pi. And then negative 2 pi. And the highest I need to go is 4, so I can go by 1s. 0, negative 1, negative 2, negative 3, negative 4. So I've chosen a good scale for my grid. Now I can plot my points. So 1 pi over 6, 2. So that means I need to go 1 pi over 6. Since my scale is going by pi over 6, that means 1 tick mark, and then a y value of 2. 5 pi over 12. Well, it'll be easier to graph this if I convert it to a denominator of 6. So I need to divide top and bottom by 2. 2.5 pi over 6. So that means go 2.5 tick marks. 1, 2.5, and then my point was up at 3. And then next was 4 pi over 6. 1, 2, 3, 4, and then my y value was up at 4. And then 11 pi over 12, convert it to pi over 6, so divide top and bottom by 2. 5.5 pi over 6. So that means 5.5 tick marks. 1, 2, 3, 4, 5.5. It's back down to 3. Then lastly, 7 tick marks down to 2. So there's one cycle of my function. Make sure you have the curved shape that cosine has. And then we could do another cycle. We could just continue the pattern. Notice it's going every 1.5 tick marks. So 1.5, it's going to be back up here. 1.5, 1.5, 1.5. And this is what another cycle of the same function is going to look like. So there's my graph of g at x. Okay, now let's move on to compound and double angle identities that you would have learned. This question says angle A is in the second quadrant, angle B is in the third quadrant. It tells us what cos A and tan B are equal to, and we're going to want to determine exact values for this compound angle and for this double angle. So to get exact values for these, we don't actually need to solve for the angle. Since we have these ratios, we can figure out enough information and use the identities for these to be able to get the exact values for these. So let's start by numbering our quadrants. 1, 2, 3, 4. And let's see what we know about angle A. So angle A is in the second quadrant. So I'm just going to draw a terminal arm in the second quadrant. And it tells us that cos A is negative 3 over 5. Well, don't forget your cast rule. Since we're in the sine quadrant, of course cosine is negative. And cosine is adjacent over hypotenuse. So 3, 5. And then what we have is tan. Oh, I'm going to label that 3 inside the triangle so we don't get confused with angle B that I'm going to be drawing. It says angle B is in the third quadrant. So angle B lies in the third quadrant, so I'm going to draw a terminal arm in the third quadrant, label that angle B. And what do we know about angle B? Tan B, so tan is opposite over adjacent, is 24 over 7. And since we're in the tan quadrant, yes, that's why tan is positive. So since I have two triangles here with two right triangles with two sides given, I could use Pythagorean theorem to actually figure out the missing side. So what I have here are Pythagorean triples actually. I could do 5 squared minus 3 squared, which would give me 16, and then square root that would give me 4. And then I could also do 24 squared plus 7 squared. 24 squared plus 7 squared give me 625. And then if I square root that, I figure out that the hypotenuse is 25. So I have all the sides of both of these triangles, so I could get any of the trig ratios I want for both angle A and angle B. So I'm going to be able to answer both of these without actually solving for the angles. So cosine of A plus B, hopefully you remember the compound angle identity for cosine of the sum of two angles. It's equal to cos A, cos B, minus sine A, sine B. So cosine of A, well here's angle A, cosine of A is negative 3 over 5, negative since we're in the sine quadrant, negative 3 over 5. Cos B, we're in the tan quadrant, so it's also going to be negative, so this is angle B, so cosine would be negative 7 over 25, minus sine A, so sine A would be opposite over hypotenuse, 4 over 5, and we're in the sine quadrant, so it stays positive. Sine B, opposite over hypotenuse, 24 over 25, but we're in the tan quadrant, so it's going to become negative, negative 24 over 25. And now all I have to do is actually evaluate this expression. So I have to multiply it out, and then I will get my answer for the exact value of cos A plus cos B. So in this one I'd have 21 over 125, negative, negative, so plus 96 over 125. So this will give me 117 over 125. So there's my exact value for the cosine of A plus B. How about sine of 2A? Hopefully you remember the identity for this is 2 sine A cos A. So 2, and then sine A, here's angle A, sine 4 over 5 stays positive because we're in the sine quadrant. Cos A, it's going to be negative because we're in the sine quadrant. Cos adjacent 3 over hypotenuse 5. So negative 3 over 5. And then just evaluate this. 2 times 4 times negative 3 is negative 24 over 5 times 5, 25. So the exact value for sine 2A is negative 24 over 25. So those are the compound and double angle identities. There are more, like we could do cos of A minus B, sine of A plus B, sine of A minus B, and we could also do cosine of a double angle or tan of a double angle. So those are just a couple practices. Another thing you would have learned how to do probably is be able to state an exact value for a ratio that does not have a denominator that's in your special triangle. So this isn't a pi over 3, pi over 6, or pi over 4 denominator, it's pi over 12. But we can actually still use your special triangles if we rewrite pi over 12 as a sum or difference of these special angles, pi over 4, pi over 6, pi over 3. So for example, cos pi over 12, I can get an exact value for this, so not an approximate decimal, but an exact value, if I rewrite this as 4 pi over 12 minus 3 pi over 12. Right? Those are both, this subtraction is equivalent to pi over 12. 4 pi over 12 minus 3 pi over 12 is 1 pi over 12, so I've made an equivalent expression. Now if I simplify both of those fractions, 4 pi over 12 is pi over 3, which is one of our special angles, and 3 pi over 12 is pi over 4, which is also one of our special angles. So now what I have is the cosine of the difference of two special angles. So I could use my compound angle identity, which would be cos pi over 3 cos pi over 4 plus sine pi over 3 sine pi over 4 to be able to get an exact value for this trig ratio cos pi over 12 by finding these four ratios from my special triangles. So I need cos pi over 3, so cosine pi over 3 is 1 over 2, so 1 over 2. Cos pi over 4 is 1 over root 2, plus sine pi over 3, so we look back at this special triangle, sine pi over 3 is root 3 over 2, and then sine pi over 4 is also 1 over root 2. And then I could simplify this expression just by multiplying it out. I'll get 1 plus root 3, and they have a common denominator. They both have a denominator of 2 root 2, so I can write it as one fraction. 1 plus root 3 over 2 root 2. If we wanted to rationalize the denominator, we can multiply top and bottom by root 2, but I'll just leave it like that for now. This is an exact value of cos pi over 12. Then you would have probably done quite a bit of proving trig identities. So A trig identity is basically an expression where the left side is equal to the right side for any possible value of a. And we need to prove that's true by showing that these two expressions are actually the exact same expression. So we do that by breaking it into two sides, left side, right side, and we'll prove that sine of 2a is actually the exact same expression as 2 tan a secant squared a. And we do that by using identities that you know are true. So sine 2a, we know the double angle identity. We know this is equal to 2 sine a cos a. There's not much else I can do to this. So what I'm going to do is now work with the right side and see if I can make this side be equal to 2 sine a cos a. So I'm going to use identities I know, like for example the quotient identity, tan a is equal to sine a over cos a. So 2 sine a over cos a over secant squared a. Well, secant is a reciprocal trig ratio. Secant is the reciprocal of cosine, so I could write this as 1 over cos squared a. Now I'm dividing fractions. So like I have 2 sine a over cos a, 2 sine a over cos a, divided by 1 over cos squared a. When dividing by a fraction, just flip and multiply. So cos squared a over 1. Right, so I haven't changed the value of anything. I've just used identities that I know are true, so I haven't changed any values. And I'm going to keep simplifying. So I have a cos squared a. That means I have cos a times cos a. So I can cross off one of those with this one. And then all I have left is 2 sine a cos a in the numerator. And in the denominator, I just have 1 times 1, which is 1. So I'm left with 2 sine a cos a. So that's the exact same as what I have on the left side, so I've proved left side equals right side. So that's how you prove a trigonometric identity. And I'm just going to quickly bring up the formula page that I give my class on the final exam. Just if you want, you could pause the video as I scroll through here, just so you can see the formulas you're given. But here's a list of trig identities that you could use to help prove more complicated identities. So at any point, just pause this and take a look at them. And it also has other formulas that we've used throughout the course. So we're using these formulas to prove other identities. Okay. Next, last thing in trig is solving trig equations. So I'll solve one linear trig equation and one quadratic trig equation. So this linear trig equation, to solve this, well, we want to isolate x, right? We want to figure out what value of x is going to make this equation true. So let's isolate x. So let's start by moving the negative 3 over 4 over. So tan x equals 3 over 4. And then in order to isolate x, since we have the ratio and we want the angle, we're going to get two answers. Remember CAST rule, C-A-S-T. We have a positive tan ratio. Tan's positive here and here. So we're going to get an answer in both of those spots. Your calculator will give you one answer by doing inverse tan, right? Doing inverse tan tells your calculator that you're inputting a ratio and you want it to give you the angle. So on your calculator, if you do inverse tan of 3 over 4, and just make sure that on your calculator you're in radian mode. So inverse tan of the ratio, 3 over 4, your calculator will give you the angle. So about 0.64. So 0.64 radians. So 0.64 radians, so remember 0, this is pi over 2 radians, pi, 3 pi over 2, 2 pi. So you have to figure out what quadrant is 0.64, and 0.64 radians would be in this quadrant here. So here is our first answer that we found. It's 0.64 radians, which means its reference angle, since it's in quadrant 1, is also 0.64. So to find your second answer, what you do is you put the same reference angle in the other quadrant where tan is also positive. So put 0.64 here, and then let's calculate how far we'd have to rotate from the initial arm to get to here. So in order to figure out our second answer, we went past pi by 0.64. So we'll do pi plus 0.64. And remember, this is just an approximate answer, but we would get about 3.78. So two answers. Both of these, x1 and x2, if you were to do tan of either of those, you should get about 0.75. Because remember, we've done a bit of rounding, but you can check your answer by doing tan of both of those, and you should get about 0.75. Let's do a more complicated one. Let's do a quadratic one. So we have a quadratic here, and the leading coefficient isn't 1 of this quadratic, so it's going to be a little bit more complicated of a factoring one. So we're going to have to factor this before we can figure out what's going to make it equal to 0, right? Whenever we have a quadratic, you're going to want to factor it. So we're going to want to find the numbers. So I'm going to use the shortcut for this one this time. So we want to find the numbers who have product of a times c, so a product of 20, and a sum of b, which is negative 9. The numbers that work are negative 4 and negative 5. They multiply to 20, add to negative 9. And what we do, since the a value isn't 1, is we divide both of those numbers by the a value, and then reduce if we can. That doesn't reduce, but this does, negative 2 over 1. And then these fractions tell us what our factors are going to be. The denominator tells us the coefficient of x, the numerator tells us what to add to it. So we have one factor of x minus 2. Well, in this case, it's a cosecant x, so cosecant x minus 2. Cosecant x minus 2, and our other factor is 2 cosecant x minus 5. 2 cosecant x minus 5 equals 0. Right, so I've factored this. I mean, we could have split the middle term and factored by grouping, but this is just a little shortcut. If we expanded this, we would get back to our original expression. Now that it's factored, we can use the zero product rule. In order for the product of two things to be 0, either this one has to be 0, cosecant x minus 2 has to be 0, or over here, 2 cosecant x minus 5 has to be 0. Those are the only two ways our product could be 0. So let's solve for both of these. So if I solve this one, cosecant x would be 2, and cosecant is the reciprocal of sine, so that means that sine x would be equal to the reciprocal of 2, which is 1 over 2. And over here, if I solve this one, oh, I forgot my x in here, I would have cosecant x equals 5, and then divide the 2, 5 over 2, which means sine x, which is the reciprocal of cosecant, would be equal to the reciprocal, which is 2 over 5. So now I have two linear trig equations that I could solve, and I'll get two answers for both of them, leaving me with 4 overall answers that would solve my original quadratic trig expression. So let's solve sine x equals a half. So hopefully you remember from your special triangle. Let me just really quickly draw the special triangle here. This is my pi over 3, pi over 6, 2, 1, root 3 special triangle. Sine of pi over 6 is 1 over 2, right? Opposite over hypotenuse is 1 over 2. So from special triangle, sine pi over 6 is a half. So what we can do is we can place that angle in the two quadrants where sine is positive, right? We want a positive sine ratio. Sine is positive in two quadrants. Sine is positive here and here. So what we do is we place pi over 6 in those two quadrants. So place pi over 6 in both of those quadrants. Pi over 6, pi over 6. And those are going to be our first two answers for x, the angles to those terminal arms, x1, x2. So x1 is just equal to pi over 6. x2, well, we fell pi over 6 short of pi. Pi is 6 pi over 6. So 6 pi over 6 minus 1 pi over 6 would take us to this terminal arm, which is 5 pi over 6. So I have two answers for x so far. This one, this one. Those are the two answers that would make this factor be 0, which would make the product be 0. Now let's look at what answers would make this factor be 0. So how could sine x equal 2 over 5? Well, 2 over 5, I can't get that ratio from any of my special triangles, so we're going to have to rely on the calculator. Now, once again, the calculator is going to give us one answer. We'll have to find the second because we know that sine is positive in two quadrants, and we have a positive sine ratio. Your calculator will give you this one. You have to use the reference angle to find that one. So let's find our first one, which is actually our third answer for x, by doing inverse sine of 2 over 5. And if we do that, inverse sine of 2 over 5, so second sine of our ratio, that gives us about 0.41, so 0.41. So there's our third answer for x, reference angle 0.41. Place that same reference angle, and we'll get our fourth answer for x, 0.41. So it fell 0.41 radians short of pi radians. So x4, we would just do pi minus 0.41, and that's about 2.73 radians. So 4 answers for x. All 4 of these answers, 1, 2, 3, 4, are going to make our original quadratic equal to 0.